Hello everyone. I am Lip Zon Hong. Welcome to IEEE ICSPC 2020. I am from University of Wollongong, Malaysia KDU University College. I am going to present about the design and modeling of brainwave-controlled intelligent prosthetic arm. The other researchers involved in this project are Dr. Ali Reza and Jonathan. Paralysis is one amongst the major neural disorder that causes loss of motion of one or more muscles of the body. People with paralysis are not able to move some of their body parts, like example, the arm. However, the prosthetic can use to restore the ability of the arm. The common electrical activity in human used for prosthetic are electroencephalography EEG, electromyography EMG, and neural signal. Next, problem statement. Paralyzed people lost their mobility of the whole body or part of body, so they are unable to carry out most of the daily activity. They rely on external devices to regain their mobility with limited movement only. Some of them cannot even use the external devices because they are unable to move any part of body. However, they still can think about the body movement, and the proposed mechanism can make the thinking into real movement. The aim of this project is to design a suitable classifier for a prosthetic arm which can differentiate the brain wave of visualization on 4 left forearm movements, which are up, down, left and right. The objective of this project is to collect the signal generated by the brain when having a thought of moving the forearm in 2 degrees of freedom, which are up and down, left and right. Then, classify the signals of every movement by using machine learning technique into 4 groups, which are up, down, left and right. In the literature review, the first part is about how the brain controls the movement of the body part. The connection of the brain and the muscle is the motor neuron. The brain will generate and send a signal to arm muscle through the motor neuron. When the brain is generating signal, the electrical activities of the brain can be captured at the skin of scalp. Besides that, there are 5 types of brain waves, which are delta wave at 0.5 to 4 Hz, theta wave at 4 to 7.5 Hz, alpha wave at 7.5 to 14 Hz, beta wave at 14 to 40 Hz, and gamma wave at 40 Hz and above. Alpha wave will occur in deep relaxation, and it will sharpen the imagination and visualization, so the signal in alpha wave can show the visualization of the arm movement. There is another brain wave called mu waves. It has the frequency of 8 to 12 Hz, which is similar to alpha wave. It is located at the sensory motor area, and it is also related to the real body movement and visualization of body movement. Next, there are 3 machine learning techniques. The supervised learning algorithm, which has dependent variable. The unsupervised learning algorithm, which has no dependent variable. And the reinforcement learning algorithm, which use the trial and error method. The current technology or related product on the market is the EMG-controlled prosthetic arm, which uses the contraction and relaxation of the muscle to control the prosthetic limb. The other technology is the modular prosthetic limb, which uses the neuron signal at the shoulder. However, the user has to undergo a surgery called targeted muscle reinnervation in order to use the prosthetic limb. The EEG headset is needed to collect the electrical activities on the skin of scalp. The Emotive Epoch Plus 14-channel mobile EEG can capture the brain wave at 0.16 to 43 Hz. It used the saline-soaked felt pad sensor to ensure the good connection between the device and the skin of scalp. The 14 channels of the headset follows the international 10 to 20 channels mapping of the brain. The methodology of this project is divided into 4 parts: dataset recording, signal pre-processing, feature extraction, and classification method. First of all, the dataset recording. The EEG device used in this project is a Motiv Epoch Plus 14-channel mobile EEG. 20 signal samples were taken for each movement visualization. The task during taking the sample is to visualize 3 times on left forearm movement for every 2 seconds. Signal samples were saved through the brain-machine interface BMI called a Motiv Xavier test bench. Second, the signal pre-processing. The signal pre-processing was done in MATLAB. The median filter is used to filter out the DC offset. The high-pass filter with 0.16 Hz cut-off frequency is used to filter out the low-frequency noise. Discrete wavelet transform, DWT, by using quadrature mirror filter, QMF, is used to divide the signal into different frequency bands. 5D composition level of QMF is chosen to obtain the frequency bands to match with the type of brain wave. There is the 5D composition level of QMF. The table shows that the CA5, CD5, CD4, CD3, and CD2 match the frequency of the brain wave which I had mentioned in the literature review. Next, the feature extraction. The signal at the decomposition level CD4 was chosen to use in this project because it had similar frequency with alpha wave. Fast Fourier transform, FFT, was performed on the alpha wave to change it from time domain to frequency domain. FFT only performed on channel FC6 and F4 because left forearm movement only can be seen at right side of the primary motor cortex. The primary motor cortex of the brain controls every body movement. The body movements controlled are different from the top to the bottom of the brain. The most top part of the brain controls the movement of the leg. As it goes bottom, the brain controls the arm and then the face. On the 14-channel EEG device, the channel FC6 and F4 is closest to the part which controls the movement of the arm. Lastly, the classification method. Two-stage binary classifier was developed in Classifier Learner Toolbox in MATLAB. First stage binary classifier is up-down versus left-right. Second stage binary classifier are up versus down and left versus right. Support Vector Machine, SVM, method was chosen because it is great for binary classifier and it is normally used to classify EEG signal. The table below shows the parameter for SVM. The kernel function is Gaussian because it works more effectively in high dimension. The kernel scale and box constraint level are 0.7 and 10 respectively are obtained through trial and error method. This is because the value cannot be too high or too low, else it will overfit or underfit. The cross-validation fold is 4. The 20 samples are divided into 4 groups, so 25% for predicted class and 75% for true class. In the presentation of data, the EEG signal collection shows the raw EEG signal. The raw signal has a range of 3900 to 4300 microvolt due to the DC offset of the device. This figure shows all the raw signal from every channel. After median filter is applied, the EEG signal has range between 0 to 200 microvolt, which is normal electrical activities of the brain. Next, after high-pass filter is applied, the low-frequency noise is cleared. After that, the DWT is performed on EEG signal to divide the signal into different frequency bands. In feature extraction, FFT is performed on the alpha wave to get the alpha wave in frequency domain. Only 8 to 10 Hz were taken in the dataset because the difference of waveform is significant at that range of frequency. The figure on the left shows the dataset for up movement and the right shows the down movement. The left side shows the dataset for left movement and the right shows the right movement. In the result, the accuracy for first stage binary classifier on up-down versus left-right is 55.3%. The scatter plot for first stage binary classifier shows it is hard to see the difference of the two groups of data with the plot. Next, the accuracy for second stage binary classifier on up versus down is 76%. The scatter plot for second stage binary classifier on up versus down shows the down movement has a higher amplitude compared to up movement. Lastly, accuracy for second stage binary classifier on left versus right is 77.7%. The scatter plot for second stage binary classifier on left versus right shows that the left movement has a higher amplitude than right movement. This table shows the complete result of the two-stage binary classifier with the confusion matrix and receiver operating characteristic curve ROC. The true positive rate TPR is the rate of the class get predicted correctly by predicted class. The false negative rate FNR is the rate of the class get predicted incorrectly by other predicted class. The positive predictive value PPV is the rate of predicted class predicted its own class correctly. The false discovery rate FDR is the rate of predicted class predicted in other class. The false positive rate FPR is the rate of class get predicted correctly by other predicted class. The area under curve AUC is the quality of the classifier. The AUC of the first stage binary classifier is 57% only, which means the quality of this classifier is low as the accuracy is low also. However, both of the second stage binary classifier up versus down and left versus right has 76% and 77.7% respectively, with high AUC value at 85% and 84% respectively. This means the second binary classifier can correctly predict the arm movement by visualization. In the discussion, the accuracy for first stage binary classifier is lower than second stage binary classifier because it consisted all the datasets for 4 left forearm movements. The similarity of the datasets for 4 left forearm movements was too high, which caused the low accuracy in first stage binary classifier. In second stage binary classifier, the accuracy is high for both classifiers because the waveform between the two classes have significant difference in amplitude. Machine learning method is required because the difference of the waveform for each movement are not significant. Due to small number of samples, the accuracy of classifier is not high. Besides that, the position of the electrodes on the EEG device were not exactly put on the primary motor cortex, which controls the arm movement. EEG artifact which generated from the human body, like example muscle movement, eyeball movement and more, will affect the frequency of EEG signal. In the conclusion, the objectives of the project were achieved. The EEG signal of the user were collected and the information of the EEG signal was extracted. The two-stage binary classifier for the 4 left forearm movement, which are up, down, left and right, was designed. The classifier can be implemented into a prosthetic arm in order to control the movement of the arm. Thank you very much.